here. Thanks for Nick for the invitation. Can you hear me all right? Okay. So I'm going to be talking about k-means clustering, which is not really a new method, but it has very old problems that are not solved, have not been solved, and probably will not be completely solved anytime in the future. So this is work that we've done, that I've done. I'm Jorge, Silva, number 3 in that list. Can you hear me now? Okay, I'll try and keep talking straight. All right, so how many clusters should be in a data set? Seems like a simple question, right? Well, it's everything but. Because it really depends on how many clusters you want and how you want to divide up a data set. Because clustering is subjective. The 2 clusterings that you see in this slide are perfectly fine, either of them. Really, it's a matter of which way you would like to divide your data. And this is something that we should bear in mind when asking for the number of clusters and whether a clustering is good or not. The answer is that there are many good clusters, and we really don't know necessarily ahead of time what the right answer is, or even if there is a right answer, because there's overlap, there might not be any clusters in your data, or the data might not be neatly divided into little ellipsoids. We saw an example of that in the previous talk. So no prior knowledge, and even what does it mean for the clusters to overlap or not? What's the distance measure that you're going to use? Is your data categorical? Because often in k-means you would like your data to be nice little vectors of scale of real numbers, and often in real data that's not the case. You have tons of categorical variables. What kind of distance are you going to define between categorical variables? So we've come up with something called the Aligned Box Criterion, and this is really we've come up with this criterion by revisiting an old method and old heuristic for evaluating the number of clusters, and doing that in a new way, given new computational resources that are available now and that were not available in the 90s and the 70s and the 80s when people were starting to look at this issue. So obviously, even though there may not be a right answer, it's good to have some guidance that you might want to divide this data into nice 2 or 3 or 15 little groups. Let me give you a little bit of background. There have been many numerical criteria, many indices, many methods for finding guidance about number of clusters. There's the Kalinski-Harbaz coming down to the 70s. The cubic clustering criterion, so Searle was at SAS at the time and still is, and is part of this work. This has been in production for, well, since the 80s. It is a method that basically relies on looking at residual sum of squares and how that evolves as a function of k. The silhouette statistic has also been around since the 80s. It has seen some revival. It has a problem, though, quadratic complexity, because one of the ways that you can evaluate if a clustering is good and if you have a good k is, okay, do I have compact clusters? Is my inter-observation distance small? Is my small within the same cluster? And between different clusters, are they well separated? But that requires comparing pairwise distances between all the points. If you have hundreds of millions of data points, that's a problem. So you don't want quadratic complexity. The gap statistic is more recent, and there have been some evolution of that. And that works as a hypothesis testing. It's basically going to tell you, okay, could this data have been generated at random from this input space? And does that make more sense compared to the clustering I found? So that's one of the state-of-the-art methods. And if you want to get Bayesian, you can look at Dirichlet process clustering, which has it's computationally heavier, but can give you a posterior probability on k, which is definitely something nice. For the purpose of this talk, we are going to assume that you're going to be using either k-means or some similar method that cares about the residual sum of squares. Is that always going to be a good choice? Not necessarily. For instance, if you're doing anomaly detection, you don't want to expect all your clusters to be roughly spherical and roughly the same size. You care about those little outlier clusters that have only a few observations. So you might want to use some variation of Dirichlet processing. But k-means has a nice property. It's actually relatively fast and scalable. So that's one of the reasons why it keeps getting used. All right, so within cluster, sum of squares is the measure that k-means cares about, that it tries to minimize. And everybody pretty much knows that k-means, how it works. It's an iterative method. It alternates between finding the centroids for points and then updating the membership function. And we might say, okay, let's just plot residual sum of squares as a function of k and pick the minimum. Not going to work, because it is a monotone decreasing function of k, which means that it's always going to, if you do that, it's always going to give you one cluster per observation. So you don't want to do that. What you might want to do is something that can be informally called the elbow method, which is basically looking at diminishing returns. Is when you increase k, your residual sum of squares is probably going to stop dropping quite as drastically. So, and in this case, it's pretty easy that 2 would be a good number of clusters, again, based only on the residual sum of squares measure. But the problem is that that plot on the right, it doesn't always look like that. Okay? So, and also, there is no, the difference between, so let's call WK that residual sum of squares that we care about. Those differences are not normalized for comparison. So, if you think about this problem as a hypothesis testing problem, you are going to be recursively testing the following hypothesis. Okay, given a candidate k, let me do the following test. Is k minus 1 or k the best hypothesis? Does k pass hypothesis testing versus the null hypothesis of k minus 1? And if I keep doing this, then it might at least give me some basis for comparison to look at. So the method that I'm talking about today, ABC, kind of follows in the footsteps of CCC, the cubic clustering criterion, and the gap statistic, in the sense that these are all methods that rely on some form of hypothesis testing, and that rely on a reference distribution where the null hypothesis corresponds to, okay, as compared to k minus 1, could this clustering have been generated by data at random? All right, so a little bit of background about the CCC, and I do apologize that the fonts got messed up in this slide. We didn't catch that. Instead of using your residual sum of squares directly, it's going to use what's called R square. Really, trace W is equivalent to that WK. So when it decreases, your R2 is going to go up, and that's what you want. That's the measure that we care about. And the formula that's kind of messed up in the bottom was devised in the 80s heuristically, because if something that SAS has, it has access to a lot of customer data sets. And by looking at lots of customer data sets and looking at the evolution of the expected R square, things like that 0.001 were not kind of pulled out of a hat, but came out of numerical simulation in lots of real examples. But this is a heuristic, okay? The CCC is a heuristic method. It's actually been used for decades in lots of business production settings. Now, the gap statistic computes the log of the ratio between, so that WK star is going to be the residual sum of squares for data that's randomly generated, uniformly at random, within the bounding box. That basically encompasses your data. The gap, so that hypothesis testing, if you do the log of the ratio, that's just the subtraction of the logs, is how much did you gain normalized for your hypothesis testing from going from doing a clustering versus just getting a uniform data generated at random. And you find k that maximizes that gap. And how do you find that W star K? With CCC, you have an expression, a closed form expression that was that heuristic. With the gap, you actually do Monte Carlo simulation. So you actually sample. You get your bounding box, and you sample a data set and run a clustering solution. And see what residual sum of squares you get for that, and that's your W star. One thing that was actually proposed in the original Tip-Shirani paper for the gap statistic was, okay, instead of doing a bounding box that's aligned with the feature axis of your data, and then doing Monte Carlo simulation, which is what the vanilla gap statistic does, we might gain more statistical power by sampling from a box that's aligned with the actual observations, right? Why is this better? Well, if you're working in high dimensions, randomly sampling from a uniform box, you're going to need a lot of samples. So doing that allows you to get more statistical power, more bang for your buck. And that pretty much was the line of thinking that got us thinking, okay, we can take this further. Instead of just aligning with the whole data set, why don't we recursively cluster our data, computing our residual sum of squares along the way? That's too close, I guess. And then cluster the sample also in the same number of groups. But then, instead of doing this, which is the algorithm for the gap, why don't we do that recursively for the clusters that we found? Okay, before I actually give you the method, a couple of observations. This is what the gap statistic plot looks like. And you can see that for that simple example, where you have that elbow, those two curves that you see in the bottom left are going to be your WK and WK star, and you're going to have a very nice maximum at 2. So this is a simple data set, and the gap statistic works pretty well as expected. If you don't have clusters in your data, so your data looks like top left, so your residual sum of squares kind of has no elbow. It's just a curve going down. And the differences between WK and WK star are much less marked. So your gap is going to look all over with a lot of variance, where those uncertainty bars come basically from lots of different Monte Carlo runs. What we do with the Aligned Box Criterion is this. So that data set, so if you can see the blue dots, that's our 3 cluster data, and the red dots are points that we just sample randomly at uniformly from a bounding box, and this one is aligned with the data set. We've done PCA here. So now try a 3 clustering solution, and the new reference distribution is going to be 3 little bounding boxes instead of 1 big bounding box. Advantage, we don't have to sample from that middle empty space that is not really going to give you any useful information. So why do this? Well, this is something like doing a recursive hypothesis test for each cluster, not just for the entire data set. And this results in a more stringent test. It's harder to pass this test. And what does that mean? This criterion tends to be smaller, so it tends to not favor large K. And that's a good thing if you think about doing model selection or doing complexity control. You want to assume that your K is not going to be huge, okay? Because you want parsimony. That's a desirable property. So let's estimate our reference distributions here. Let's see what we get. 1 box. Then you move to your next candidate, K equals 2. You have 2 boxes. It looks like this. This is your reference distribution for K equals 3. You have a range of candidate Ks that you sweep. 4, 5, and you keep going until you get to a point where really you can no longer distinguish. Okay? And so you're going to be clustering each of those candidate solutions, and you're going to have your reference distribution be dependent on K. And that's the main innovation here. Your reference distribution changes with your candidate K. What kind of results do we get? Well, this is the gap statistic for that 3-cluster data set. On the left, we get WK start to decrease faster with our aligned box criterion. And we get a much more clear maximum that happens to be a global maximum in the right-hand side panel, as opposed to the maximum that's only a local maximum on the left-hand side. And yes, there was a big jump from 2 to 3. It's clearer on the right-hand side. And also you see something interesting. Look at that little dot at 6. That's actually not a bad candidate solution, because if you look at the original data set, and I'm going to go back a little bit, K-means usually likes clusters that are kind of spherical. This is not a spherical data set. This could easily be 2 ellipsoids on the top, 2 in the middle, 2 in the bottom. Okay, so 6 is actually not a bad solution. Right, but this is a toy example. So let's get into some more challenging examples. 7 overlapping clusters. And here, basically, they perform a lot more similarly, but again, the ABC tends to have a couple more obvious maxima. And now some real data. We actually did this on a Kaggle data set, which is a claims prediction challenge data. And we used a number of implementations. We used the open source integration node to call R for the gap statistic. CCC is actually available in proc fast class in SAS. The ABC is implemented in the distributed version, which is we call proc HP plus, and we ran it. This is the CCC, so cubic clustering, and it finds 2 and 8. Note that there really aren't a lot of, we don't know the real K for this data set. But the gap statistic seems to find 3 and 9. So again, 2 relative maxima. The ABC agrees with the gap statistic, but does so in a way that's a little more obvious, and also says that 3 might not be a bad idea. So in this sense, remember that CCC was looking at 2 as well. So a couple of properties, really, that we care about in this method. We care about that regularization effect of not favoring large K. We care about scalability. How does the complexity, the runtime, increase with the number of observations? And we care about stability in the results. We care about because k-means, as everybody knows, depends on initialization, and we can easily get a bad k-means solution. How does that impact your criterion? So we made multiple runs, and you can see that the plot doesn't go all over the place. It's pretty consistent given different initializations. And the more runs you make, the less your variance, which is kind of obvious. Also, in the Kaggle claims prediction challenge, we get very clear if you start doing multiple runs and counting how many times ABC found particular K to be the best, you get a nice kind of Poisson-shaped distribution, which is what you would want. Okay? So stability is good. Scalability is good. What we don't want is to see a polynomial going up. You don't want quadratic complexity as a function of your sample size. You want nice linear scaling with number of observations, which is what you get here. So, and the two colored curves are for maximum candidate K equals either 10 or 20. So obviously the higher the K that you sweep, the longer you're going to take. Stability also. So for a known reference data set where we know which are the cluster assignments that are good, we computed accuracy as percentage of the times that the percentage of the points that were correctly assigned to their correct cluster. And we see also as a function of the sample size that we are doing well. And for the parallel implementation, and let me see how I am on time. Okay. Okay, so basically the nice thing about So this is obviously always going to be slower than just doing the gap statistic because you are computing aligned boxes for all the clusters. But the nice thing is you can parallelize this. You can distribute the computation of the reference distribution across nodes. And I'm going to be stepping quickly through this. There will be an archive paper that you can see, look at details, and I'll just go and one of the things that can be parallelized is definitely your XX prime, and remember that your SVD is not going to be done on the whole data set, but on the localized clusters, so that's going to be faster, and moreover, we can use stochastic SVD, which is pretty fast even for a large number of points. So basically, take-home message. We have better defined maxima. We basically favor smaller values of K, clearer peaks, stability, and scalability. Those are some properties that we find desirable. And if you're using K-means, that's something you might care about as well. Thank you very much.
Thanks.